And the voltage coil for wattmeter 2 is connected between Y and B. All right, so we know that Y is at the positive potential, B is at the negative potential. Y is at the higher polarity, B at the lower polarity. All right, so we need VYB, but we know that already because we have defined that from before based on our phase sequence. So we have defined certain voltages already, VRY, VYB, and VBR. All right. Now, wattmeter 1 said, well, we need also VRB. So, all right. Now, the next thing we needed to do was to find the phase currents. In order to find the line currents, and since it's an unbalanced system, we need to find the phase currents. We need to find all phase currents. All right? Everybody clear?
Yes, sir.
Sir, where have to find all phase currents again, sir?
Because we need line currents. Right. We're to find the line currents without knowing what the phase currents are. Right? And since it's an unbalanced system, it's important now that you find the phase current in each phase. With me?
Yes, sir.
All right. Now, since it's they tell us now that the loads are non-reactive. So the question state them as non-reactive loads. Now, we know that non-reactive means that there's no inductance or capacitance in the load, which means then that it is purely resistive. A purely resistive load. Now, for a purely resistive load, so this is something that you need to know too, and always bear in mind. For a purely resistive load, the voltage phasor and the current phasors are in phase. Everybody clear? For a purely resistive load, the voltage phasor would be in phase with its corresponding current phasor. So for example, VRY is the voltage phasor for the red yellow phase. And IRY would be the current phasor for the same red yellow phase. Now for when the load in the red yellow phase is purely resistive, then VRY and IRY are going to be in phase. Everybody with me?
Yes, sir. It makes sense because the reactive portion would be 0.
Right. All right. And this follow on from something that we had done with the impedance triangle and those things from the first week. All right. But yes, so bear that in mind. And we can then write down the formula for power. We know what the formula is for power. It's VI cos theta. Remember? Power in per phase is V phase, I phase, cos theta for that phase. The phase difference between the voltage phasor and the current phasor. All right. So we are being specific now when we state the phase. So it's VRY and IRY and cos theta VRY minus theta IRY. All right. Now we know that these for VRY and IRY are going to be at angle 0 because VRY was chosen as the reference, so it's at angle 0. So therefore IRY is going to be in phase with it, and it's going to be at angle 0 too. All right. Now cosine of 0 is equal to 1, right? So that's why we end up with PRY is equal to VRY times IRY. So you could imagine that a times 1 is right here. It wouldn't change the thing, right? By the way, if you're writing the formula for power, if you're not writing I square R, make sure you write VI cos theta, right? Even if cos theta is 1, show me that you know that it's going to show me how you get it to be 1. Don't just assume that I know, because I usually forget everything at the most inappropriate times, like when marking papers. So we have a formula for the reactive, non-reactive load in our yellow phase. Similar equations can be written for the YB phase and the BR phase, because they are also purely resistive loads in those phases. Body clear?
Yes, sir.
Good. Conroy?
Yes, sir.
All right. All right. So we define our voltages, and we need now to work out, and we'll define what the formula for the power is in each phase. So we need now to work out the current that is flowing in each phase. So the current in each phase, we are used to saying IRY, but notice that they have labeled it as I1. So I just use that also, right? Which is an important thing to do. Refer to, when you're referring to your circuit diagram, you should use the labels that you have there, right? So I1 has a magnitude of 25 amps. And because we know it's in phase with VRY, its angle is going to be 0 degrees. So it's 25 at angle 0 degrees. We can work out I2, which will be the current flowing in the yellow-blue phase. So it's the P yellow-blue divided by V yellow-blue. And that gives us 15 amps. So I2 is 15 at angle 240 degrees. Clear?
Yes.
All right. And I3, similarly, we'll work it out same way. PBR divided by VBR. And that gives you 10 amps. And 10 amps at angle 120 degrees. All right. And by now you would know what each wattmeter is reading in terms of current and voltage. All right. So that's what is stated here. All right. So far we have we need now to take stock and see what we need to find. All right. So we need to find IR, we need to find IY, and we need to find VRB. We already have VYB, so we need to find VRB.
So, sir, so this
Yes.
means that if, so wattmeter 1 was, the current coil was in the blue line, we would need to find IB.
Right. And in that case now, you would need to put the command line somewhere else.
Yes, yes. All right.
All right. So in the lab experiment that we do with the 2 wattmeter, we usually connect between red and yellow. Right. So yellow becomes the common one, and so 1 wattmeter current coil is in the red line, and the other wattmeter current coil is in the blue line, and yellow becomes the common. So you decide which one you want to choose, and any one of them you choose, you just know anyone you choose as the common, you just know that the current coils will be going in the other 2 lines. All right.
Yes, sir.
All right. All right. I just remembered a joke Well, I won't share it because it might bring somebody into disrepute. There's nobody in this class though.
I can't share it, sir.
No, there was somebody who knew of what was done in the lab, and so I figured out, but that's the only way it could be done. And so I had given a question kind of similar to this in a test, and he was there saying, "No, this can't work. This can't work because that's not how we do it." I said, "No, just follow the instructions say and do it." And
I think we have an idea, sir.
he probably spent about 3/4 of the exam just sitting down and said, "No, this can't work."
Oh boy.
You know?
So we need so that means we need to switch them around and try to work it. Oh boy.
Well, no, look, right, yeah, you can do that too, you know. Yes, you could do that, right? Anyone you choose as a common, you know that the other two now would have the current coils in them. All right, so anyone can be chosen. All right. All right, so we needed to find IR. So we'll go back to Kirchhoff's law now and look at what's happening at the nodes. So IR plus I3 would be equal to I1. So therefore IR is equal to I1 minus I3. Right, and that works out to be 31.225 at angle minus 16. Then we need also to find IY, which is flowing through wattmeter 2. So IY is equal to I2 minus I1, and that works out to be 35 at angle minus 158.21 degrees. All right, and remember
Sir,
Mr. Atkinson, you need to mute your mic.
ask me something, sir. Why wouldn't we need to find IB again?
Say that again.
Why wouldn't we need to find IB?
All right, what is IB doing? It not doing anything in terms of the watt meters. All right. Remember, so we only need to see what is happening with each watt meter. Okay. All right, so we need to find VRB, and VRB is actually minus VBR. And one we are working it out is to say, all right, what is angle for VBR? And take 180 degrees from it, because 180 degrees would make an about turn, right? Going in the opposite direction. So when I take 180 from 120, I get minus 60. All right. And if you the Cartesian map or the Argon diagram, you will see that minus 60 will be opposite to 120. A straight line down. If you use a protractor measure, you will end up at minus 60, which is also equal to 300, right? 360 minus 60 would be 300 degrees. So I could have written it as 400 angle 300 degrees. All right, so now we have gathered all the data that we need to find in order now to be able to solve the problem. Find the power in each of the watt meters, read by each watt meter. So the power read by watt meter one is VRB times IR times the cosine phase angle between two lasers, between IR and VRB. All right, so that's what this equation is saying. All right, so VRB is minus 60 and IR is minus 16.1. So we put in the data, 400 times the 31.25 times the cosine of that, and we end up with almost 9,000 watts. $8,999.683. All right. Also, so we find out what meter one is reading. We need now to find out what meter two is reading. So we go back to the equation that is governing its operation. So it's VYB times IY times the cosine of VYB, cosine of the angle for VYB minus the angle for IY. All right. All right, and then we work out, substituting the data that we know. VYB is at 240 and IY is at minus 158.21. Minus and minus will give you a plus here. So you find the cosine of that sum here.
Sure.
And then you work it.
So we
Yes.
didn't have to change to put a minus before this voltage because it already match up with the phase sequence.
Right. Right. It's with in the sequence, right? Yeah, this one is VYB. So, and we had defined what YB was already.
Yes.
We had 400 at angle 240.
Yes, sir.
All right. Right. So with the sequence here, you work with the sequence that we have defined, and if we don't have any, we work to find those that are the one that we need to find. So one of them is going to be opposite to what we normally use. All right. The total power in this circuit then is the sum of each wattmeter readings and give us its watt. And this is a verification of the phase value of the load in each phase, right? We know that this was 10, this was 6, and this was 4. If you add up all of them, you get the 20. So the wattmeter and the 2 wattmeter method verifies what we know as the phase value of the load. So we can say that the 2 wattmeter method was able to determine the total power in a 3-phase unbalanced delta circuit. All right. So the next question now, which is what I wanted you to do, is a balanced star connected system, 3-wire star system. So let's see if we can work out what the total power is in this 3-wire system, 3-wire star connected system. All right, so let me give you about 10 minutes then to try it.
All right.
All right, so let's talk to it first though, so that everybody can get a good start. What's the first thing that you want to do? So yeah, the procedure that we normally employ when we're going to deal with any one of these problems.
Right on what you have.
Good, right on what you have, yes. All right.
So find the phase currents.
Right. So you need to find the phase currents, good. Right. And then?
So you figure out what the wattmeter needs.
Good. right. Yeah, pick a reference. All right. So what's the reference for our stars?
Red phase, sir.
And
Red phase current or red phase voltage or
Red phase voltage, sir.
right, red phase voltage. All right. So good. All right. So it sounds like you're on the right path.
sir,
I'll give you 10 minutes.
sir. The
Yes.
wattmeters are measuring active power, right?
Yes, yes.
We just need to the load is both reactive and active.
Yeah.
And so I kind of do we consider the reactive as well, or we just in terms of current, do we consider only the resistive part of it, since the wattmeter is measuring the active part of it?
No.
Okay, so we still use it to the whole load.
Right. Yeah, I guess the watt meter is smart enough to distinguish between real and reactive.
All right.
to have Duncan go through.
Sir, all impedances are the same, right?
This, right?
Yes, yes.
So we
Right. They say each branch consists of a coil of resistance 4.2 ohm and 5.6 ohm reactance. All right, any progress?
Just able to find IR. Me not know if it's correct.
Okay.
So,
All right, let's see if it is.
32.86. But you have, but me not have the angle. Me have minus 23.13. 0.13.
Hold on, I wonder if I put it in the wrong.
But I have
No, sir, I got the
230.
same thing that you
Oh,
got.
It's 5.6, man. Yeah, 5.6. Right. Yeah, so the impedance should be 7 at angle 53.13.
I have
Sir.
one of it. That's one.
Yes, it's a Bruce.
Sir, I just use the rectangular form, you know, sir. But the currents are different.
The current.
In calculating, yeah.
I'm not sure what I mean.
Sir,
Difference in
balance system, but the mood of the currents I got are different.
Oh, but all right. So let's follow this then. Sorry. The phase voltage would be the line voltage divided by √3. Everybody with me?
Yes, sir.
Yeah.
All right. And then we're going to, as usual, VRN is our reference phasor for the star system. Rn is 230.94 at angle 0. Therefore, Vyn is 230.94 at angle 40. And VBN is 230.94 at angle 120. All right, now the same impedance is in each phase, right? So ZR is equal to ZY equal to ZB equal to 4.2 plus J 5.6. And that works out to be 7 at angle 3.13. All right, so if I want to find IR, it's VRN over ZR. So it's a 230.94 at angle 0 divided by 7 at angle 53.13. And that works out to be 32.991 at angle minus 53.13.
Sorry, if I get
All right.
34 for
So-
the magnitude, that's too much off.
Yeah, man, because you would have done some bad rounding off somewhere. What do you use as your phase voltage?
230.940.
And what you got to the phase impedance?
I use the same 750.130. The only difference is that I use 3 decimal places.
But even so, you wouldn't get up to 34. So you got a 230.94 what?
Yeah.
No man, so it wouldn't make any
Alright,
difference.
man. I'll try again.
Just something wrong with the maths there. All right, so we work out IR, and we do a similar thing for IY.
Okay.
So it's VY divided by, I had ZR, but it's ZY and ZB. But you know, they are all the same anyway. I never said that before. But they're all the same. The same, all the impedances are the same. So if I'd write ZY here, to be more accurate, it should be ZY, and for IB, ZB. But they all have the same values anyway. Because we had stated before that ZR is equal to ZY equals ZB.
Sir, for
It can,
I added 362 because I got
Minus 170.
the angle, the minus 173.13. I added 360 to that.
Okay.
yeah, you could do that.
Okay.
But what I did was just take 240 minus 53.13. Because when you're dividing, you subtract the angles. 240 minus 53.13. So that's how I end up with that.
All right, sir.
All right. And IB is at angle 66.87.
Oh.
All right. So what meter one reads IR and VRB. And what meter two reads IY and VYB. All right. We need to find VRB and VYB. All right. So we hadn't found any line voltage before, but we now need to find them since the wattmeter is reading those. VYB for wattmeter 2 and VRB for wattmeter 1. So VRB would be equal to VRN minus VBN. Remember? So when we were defining our line voltages for the star system, you know, you take the first one minus the second one. So VRN minus VBN. So VRB works out to be 400 at angle minus 30. Everybody with me with that?
Yes, sir.
Sure.
Okay. So Powell, all right. So VRB is at 400 angle minus 30 volts, right? And minus 30 is also 330, right? From the positive side. Okay, Mr. Powell. All right, and VYB would be VYN minus VBN. So we just substitute in the values for VYN and VBN. So we get VYB is equal to 400 at angle 270. In your calculator, you might see minus 400I.
Is that the same
Or if you use
as
this number.
minus 90, sir?
Right.
Okay.
0 going, right. Yeah, minus I would be minus 90. Remember, I is angle 190 degrees, 1 at angle 90 degrees. So minus be 1 at angle minus 90 degrees. Or 270 if you're measuring anti-clockwise. All right, so again, now we go back through now and we start to calculate the power read by each wattmeter. So wattmeter 1 is reading VRB times IR times the cosine of the phase difference between those two phases. So it's 400 times 32.991 times cos of VRB was at minus 30 and IR was at minus 53.13. So we get wattmeter 1 reading 12,135.62 watts. And wattmeter 2 will be reading VYB times IY times the cosine of the angle, the phase difference between those two phases. All right. So VYB is at angle 270 and IY is at angle minus is angle 186.87. This is IY. All right. So the wattmeter 2 is reading 1,578.51 watts. Everybody okay with that?
Yes, sir. So what I got, sir.
You got it. All right. Good.
Slightly off, sir. But yeah.
How slight?
Just I got for PW1, so I got 12,135.8, and then for PW2 I got 1,578.53.
Okay. All right. Well, we wouldn't split hairs about those. Yeah, that's all right.
All right, sir.
All right. So we add them up and we get the total power. And it works out to be 13,714.13 watts. All right. Or you could write it as kilowatts, 13.714 kilowatts. By the way, when you change from watts to kilowatts, do it way at the end. It's right at the end you should do it. Don't bother do it from way up here, so, because you start to rounding off when you do that and lose some accuracy. All right, so let's verify what we have. We know what the phase power was, 3 VR we used for the red phase. It's 3 V phase, I phase, cos theta for that phase. So 3 VRN times IR cos theta VRN minus theta IR. All right, so 3 times the 230.94 times the 32.991. VRN was at angle 0 and IR was at minus 53. So the total power using what we know from before is 13,714.13 watts.
Sir.
All right. Yes.
Sir, the voltage we using the formula to find is the phase voltage, right, sir?
You mean for this second one here? We're not doing the verification?
No, sir, for wattmeter 1.
No, man, it's a line voltage. Look at it. It's between red and blue, you know. Remember the voltage between any two lines is a line voltage.
Okay.
And the same thing with the wattmeter 2, BYB. So using the 2 wattmeter method, you're actually using line current and line voltage. Line current. So for a star system, a line current is also phase current. Right? But line current and phase and line voltages are being used in the 2 wattmeter method. All right. Now, sorry. We can actually find the power factor of the system by using the wattmeter readings. These formulas tell you how to do it. The book has some proof, but I don't think you really need to know the proof. You only really need to know how to use the formula. All right, so it's a little bit kind of unwieldy, but let's say you find the total power. All right, so that is one thing that's called PT up there. You find the difference between the 2 wattmeters, and you use the larger readings as the PW1. So whatever your findings were before, you use the larger reading as PW1, and then you take away PW2 from that, multiply that numerator by √3, and you get a value. Then you take the tan inverse of that value, and you get an angle, and then you find cosine of that angle, and you get the power factor. All right. It's all more complicated than it is, so let us look at an example quickly. All right, so 2 wattmeters connected to measure the input to a balanced 3-phase circuit indicate 2,500 watts and 500 watts respectively. Find the power factor of the circuit when both readings are positive, and B, when the latter reading, so that will be the 500 watts, is obtained after reversing the connection to the current coil of one instrument. All right, so some of you who may be familiar that sometimes when you're reading the wattmeter, you might see the needle deflect towards the left, like it's trying to go below 0. And if you flick the reverse switch, then you get a positive reading. So that's what part B is saying. When they when they flick the reverse switch, it got 500 in part B. So let us look at part A first, though. All right. So the total power according to wattmeter readings would be the 2,500 plus the 500, and that will give us the 3,000 watts. All right. Then theta now would be equal to the tan inverse of √3 times PW1 minus PW2 over PT. So you could have made this a 2-step process like we did before. Find tan theta first, and then afterwards you'll find the theta. Yeah, maybe that's better. You do it that way, so you don't mix any mix up.
If you use radians with that, sir.
No, man, straight. Degrees. So √3 times it, 2,500 minus 500 divided by 300. It works out that the angle is 49.107. And then I find the cosine of that 49.107. And that works out to be 0.655. All right, the thing with this, though, you can't tell whether or not it is a lagging or leading power factor. We're just using the readings. I guess we'd have to know exactly what make up the load in the circuit to know whether or not it's lagging or leading. But the calculations alone won't tell you whether it's lagging or leading. All right. Now for part B, where the 500, you had to reverse one of the wattmeter current coil to get the 500. So, which means that in reality, PW2 is actually reading minus 500 watts, right? So the total power then would be this 2,500 minus the 500, give you 2,000. And then we go back through this again. But in this case now, the numerator is going to be larger than the denominator because you have a minus and a minus. Two minuses give you a plus. Right? So the angle works out to be 68.948 degrees, and the cosine of that angle works out to be 0.359. All right, so practice. Oh, you have a lot in the bird. You can get a lot of practice from these. So check the bird and read them and practice them. Finding the power factor from wattmeter readings. Where am I? Sorry. All right, power factor correction. Any questions on finding the power factor from the 2 wattmeter readings? Supposed to be fairly straightforward.
Yes, sir. Pretty straightforward.
Right. All right. Now, why do we need power factor correction? In industrial plants, usually have a lot of motors and loads that are highly inductive. And because of that, now the power factor is usually low and is a lagging power factor, and it can become very poor. So anything below 0.8, would be considered fairly poor, and the lower it gets, then it's bad. So for example, the 0.36 here would be very poor. Even the 0.655 here would be poor. All right. Now, a poor power factor is also a costly thing and very inefficient. So, usually, plants try to make some effort to correct their power factor, and the public utility like JPS usually give people an incentive to correct their power factor, to have better power factor. The incentive basically is that you pay less for your bill, your light bill, and your power demand and all those things. So there's an incentive to have a better power factor. Plus, you want to improve your operational efficiency. All right. Now, the equipment that is used, one equipment that is used is a capacitor. All right. And I'm showing you some capacitors. So this will be a bank of 3 capacitors on a power line. Right. These cylindrical cans are transformers. So the capacitors are connected close to the transformers, usually connected close to the loads. Right? So when you're out on the street, you can look up and see, if you see these kind of rectangular shaped boxes, these would be the power capacitors. All right. For 3-phase system, it's usually referred to as a 3-phase bank, or a bank of 3. All right. Now, circuit diagrams to show you how capacitors can be connected across. So they are connected in parallel with the load. So in both cases you have a delta connected load, and in this case here on the left you have delta connected capacitors, while on the right you have star connected capacitors. All right, so correcting the power factor means bringing the power factor closer to unity, closer to 1. All right. And I think I was pointing out that the load can be either star or delta connected. It doesn't really matter. And the capacitors can be connected in a star or delta also. All right, now this diagram, which consists of two right angle triangles, essentially explain what is happening when you're doing power factor correction. All right, so this larger triangle that comprises S1, P, and Q1 is the system power triangle. The system power triangle before you do power factor correction. So the power factor angle was phi1 for that original system. Now after you do your power factor correction by adding some capacitors or reactive power, capacitive reactance, you end up with this smaller triangle described by S2, P, Q2. All right, and you notice now that this angle is smaller, and the cosine of a smaller angle is actually a larger fraction. Right? So the original system had this power factor P over S1, and then after the power factor correction, the new power factor will be given by P over S2. Right? So QC here is indicating that some capacitive reactance was added. Right? Reactive power due to the capacitor was added. All right. Now, if you remember how we draw the triangle, QC for the capacitor would be below 0, would be on the negative pole of the imaginary axis, right? So that's why this R of a Q is going down, right? Basically what we do, we add Q to Q1, QC to Q1 and end up with Q2, right? So that's what this is saying. Q1 plus QC, so QC is a negative number, you get a lower value, right? Something else that you will need in your calculation is to know that tan of phi 2 is equal to Q2 over P, because sometimes you will need to know what. Yes.
Could you go over that last part? I didn't quite got what you said about the Q1 plus QC part. I don't understand how that one happened.
All right. So if you remember from the first week, for a capacitive reactive power, the triangle is actually upside down. So QC would be vertically down on the negative imaginary axis. So minus J, Q will be on the minus J axis. QC for the capacitance. And S2 would, and S for the capacitance would be below here, right? So P would be real, QC would be minus on a minus J axis, and S would be
Right, so
negative.
Q1 is real and QC is imaginary. Okay.
No, man. Q1 is also imaginary, but it's positive. This vertical line here is your imaginary axis.
Oh,
P is the real, Q is our imaginary. But you have positive imaginary, like Q1, and you have negative imaginary, like QC.
Sure, the positive aspect of it would behave like inductance, and the negative aspect would behave like would basically represent the capacitor, the reactive capacitance.
Right, right.
So, sir, is there a possibility that the triangle, you could add enough capacitors to the thing and bring it down, bring the diagram to a point where there's no inductive reactance?
Yes, right. There's no reactive power. Right. Yes, you could do that. There's so that in that case now S2 would be equal to P, right? Because remember S is equal to P plus JQ. Do I have that somewhere here? S is equal to P plus JQ. So if there are no Q's, then S and P would be equal. Right? Yes. So yes, it is possible. But then there's also a cost factor that you have to consider. And so one of the things that you have to consider now as the engineer would be, is it worth power factor to unity? Can I afford it, or can I live with a 0.95 or some other value? So that's one of the questions that you would have to ask yourself. But theoretically, it's possible.
Yes, sir.
All right. Good. All right. So let's do a quick example. So 3 similar coils, each having a resistance of 4 ohm and an inductive reactance of 3.46 ohms, are connected in delta across a 400 volt 50 hertz 3-phase supply. All right. Everybody seems to like the 400 volts system. The Bird likes it. The Hughes likes it. I think maybe only the Wiley might give you some different values. All right, but anyway, it doesn't really matter. All right, so the question asks now to find the total real power drawn by the coils, the total reactive power drawn by them, and the apparent power drawn by them, the power factor of the coils, and then the reactive power supplied by a bank of 3 delta connected capacitors, which are designed to raise the system power factor to 0.85 lagging. All right. And then we must find the apparent power of the system after power factor correction. All right. So I could have just asked you to find this, because many times, many questions just go straight to this. Find the reactive power that will be required to raise the power factor to the 0.85 lagging. But I'm asking the question in such a way that you can see some other things also, right? Because you would still have to work out these even if you were not told that you need to work them out. All right, so let's get going. All right, so everybody understand the question. We have a load here, 3-phase load. Apparently the power factor is not what we would want it to be, and we want to raise the power factor up to 0.85 lagging. All right, so one of they ask us to do certain things, including finding the power factor of the existing system. All right, so as usual, let's get into what we know. So we know that Z is equal to R plus JXL. And so that was given 4 plus 3.46, J 3.46. So the impedance in each phase is 5.289 at angle 40.86. All right. right away I can tell what the power factor could be, or how to find the power factor. But we'll get into that a little more. Anybody know how you could find the power factor just from what we've talked about already?
That angle, sir, just cost the 40.86.
Right. Very good. All right, so this is a delta system and VL is equal to V phase. All right, so we're using one phase since the system is balanced. We're going to use VRY as our reference phasor. So VRY is 400 at angle 0. So IRY, we don't know which one is R and Y, I think, but we just, I should have put on some labels on these. All right, IRY is VRY over Z. So it's a 75.631. That's a current at angle minus 40.86. All right, so this is how you do it. 400 angle 0 divided by Z, 5.289 at angle 40.86. Current, phase current of 75.631. All right, now the total power, since it's a balanced system, we just need to find the power in one phase and multiply by 3. So the total power then would be 3 V phase, I phase, cos the cosine of the phase angle between the current and the voltage phasors. So it's 3 times 400 times the 75.631 times the cos of 0 minus 40.86. All right, so the total power works out to be 68,640 watts, right? Or 68.641 kilowatts. So the first question was to find the total power. So we have done that. Then the next question was to find the total reactive power of the existing system, right? So we have not looked at what the capacitor is doing yet, right? So reactive power is given by 3 VP IP sine theta, right? So 3 VR IR sine theta VRY minus theta IRY. And that gives me 59,000 VARs, right? 59.375 kilovars. All right, then we're asked to find the apparent power of this system. So ST would be, one way of doing it is PT plus JQT. I could have found 3 V phase, I phase, and that would give me the answer too. All right. So S is equal to P is a 68.64 and J is a 59.375. So ST is 90.76 at angle 40.86 kVA. Right? And then power factor from the power triangle is equal to PT over ST. And it's a 0.75, it works out to be 0.7563. And since we know it's an inductive load, we know it's lagging. Okay. We could also have found it this way using the value of the impedance. The impedances, resistance and impedance. And that gives me that also. Or we could find the cosine of the angle for the impedance, or the cosine of the angle for the apparent power. Both of them give me, all of them give me about the same thing. So several ways of working out the power factor. All right, so the power factor is 0.753 lagging, and they want to raise it up to 0.85 lagging. All right, might not look like they're going very far, but it's just the procedure we want to see how it's done. All right, so the power factor of the new system now, which would be cos theta 2, instead of phi 2 here, I'm using theta 2, since we have been using theta for our power factor from before. So the cos theta 2 would be 0.85 lagging. That's the power factor of the new system after capacitors are added. So theta 2 now works out to be 31.79. So remember, theta 1 was 40.86. Theta 2 now is 31.79. All right, so we can use that value now to find out what Q2 is, the final value of Q for the new system. All right, so tan theta 2 is equal to Q2 opposite over adjacent, or rise over run. So tan theta, so Q2 then is equal to P times tan theta 2, and that works out to be 42,539.6 VARs. Right? Now QC is the difference between QT and Q2, right? So QC, which is what the capacitors have added to the system, is 59.37 minus 42.5 kVARs. So Q is equal to 16,834 VARs, or 16.835 kVARs. So that's what QC is equal to. Now, they want now to find the new apparent power of the system. So the new apparent power would be the PT plus the JQ2, and that works out to be the 68.64 plus J42.54 gives me 80,753.66 at angle 31.79. So the new apparent power is 80.754 kVARs. So adding the adding the capacitors has reduced my apparent power demand from 90.76 to 80.754, and it has improved my power factor from 0.75 to 0.85. All right.
This question is well involved, sir.
Yeah. Yeah. All right. For your homework, I've given. There are some additional things I want you to do on this question. So the data is there before. Come on. Mouse not going back. All right, so the data is there from the problem. So what I've done now is to just ask some additional question, simple question. What is the line current before we did power factor correction? And what is the line current of the system now after power factor correction? And then this one, so those will be very simple. And this one, the capacitance per phase for the capacitor bank. So that one I gave you the answer. And here you can state any benefits of power factor correction that you have observed in this problem. All right, so that's something that you have to do tonight, along with, let me hear what somebody's saying here. When is the first test? I don't remember. I'll look on it on the schedule. I told myself today that I need to look back on the schedule. All right, so it's on the schedule. I just need to consult it. You can do so also. It's in the Google Classroom. All right. Come on. And then I have two questions here for your practice. All right. You can try start working them for tonight, and we can go through them in the tutorial tomorrow. Somebody's asking me what's the code for the Google Classroom. Send me an email if you haven't been invited yet. Tell me which class you're in and your ID number and email address and all and those things. And I will send you the link. I'll send you an invite. All right. Any questions? So one of these questions was taken from the Hughes and one was taken from the Bird. So if you go and practice in the 3 books, you should be all right also. All right. Any other questions?
Not at the moment, sir.
Yes, sir. When is the first test?
All right.
You hear me, sir?
Yeah, I thought I just said that a while ago.
Didn't hear you, kind of tripped up.
Oh, you kind of chip out. Check the Google Classroom. It's in the schedule.
All right, sir. Thanks.
I don't. I mean, answering like that because I don't remember. I need to go back and check myself.
All right,
I
sir.
know it was. I know it wasn't in week 3, so I wasn't too concerned about this week. But maybe next week you should look, right? You should check to see if it's next week. All right. All right. If there are no other questions, I think we can call it a night until tomorrow. So you have lots of things to
Sir,
do.
how will the test be administered?
Yes, sir.
I don't know yet. They were supposed to be setting up Moodle for me. That hasn't been done yet, so I don't know yet. But you would know it in early enough time.
Some of us still can't access Moodle as well, sir.
I can't really either. I don't think my thing has been set up for Moodle either. So yeah,
Yeah.
in previous times, basically what I've done is send you our tests, and you do it and send it back to me. So we would have like a class and send you the test, give you a time to do it, and you submit it as soon as possible after that. Scan so you'd have handwritten it, scan it back, and send it back to me. So that is the option that we might be considering, unless Moodle comes up for us.
Okay, sir.
All right. All right. Sorry, I can't be any clearer yet, but I kind of waiting to see what will happen with Moodle also.
All right, sir. Enjoy the rest of your evening.
All right. All right. Same to you and to everybody. Have a good night. So this is in the Google Classroom, whether it's the U1 associated with UTech or my personal one. As I said, anybody who doesn't have access to the Google Classroom is probably because you have not been invited. So just send me an email. I've invited all those who have had email addresses for. So you can send me and I will send you an invite from both classrooms. Any one of them you can get into. You just work with that. All right.
All right, sir.